Hi, I'm Alex Stegling, and I'd like to tell you about my research, which in a nutshell is summarized by this illustration. So every now and again, blasts of solar wind plasma from the sun impact the magnetic field surrounding the Earth, which further compresses the day-side magnetosphere and stretches the night side. And this also launches global-scale ultra-low frequency waves into the magnetosphere. These waves have a number of important effects. For example, relativistic electrons gain energy from these waves by resonantly interacting with them or surfing on them. For this presentation, I'd like to focus on the physics of the waves themselves. The theory for describing ultra-low frequency waves, or ULF waves in the magnetosphere, is called ideal magnetohydrodynamics, or ideal MHD. This treats the plasma as a perfectly conducting fluid with a mass density, a flow velocity, and a pressure. The electrical properties are summarized by Ohm's law, which is given by E plus V cross B equals 0. This has an important implication known as Alfvén's theorem, which answers the question, by how much does the magnetic flux through a surface change as the surface moves with the plasma flow as a function of time. It can be shown that for ideal MHD flow, the change in magnetic field according to Faraday's law is balanced by the change in the area of the surface under the flow. So the total flux remains constant. Further, it can be shown that the plasma flow velocity can be taken as the field line velocity. This is useful for interpreting the plasma motion and understanding how waves are generated. To consider waves, we need to work out what generates the restoring force. For this, we need the fluid equation of motion. For example, in a neutral gas, ignoring viscosity, Euler's equation tells us that the pressure term gives rise to acoustic waves. For an ideal MHD plasma, the flow of currents gives rise to an additional force given by J cross B. This term can be derived by combining the Lorentz force equations for the ions and the electrons. Using Ampere's law and a vector identity, we can rewrite this equation in the following way. Here there are two terms on the right-hand side which give rise to distinct wave types. The first term shows that the magnetic energy density, or magnetic pressure, plays the same role as the kinetic pressure P in this equation. This is actually the dominant term in my area of interest, which is the inner magnetosphere. In this case, compressive flows push field lines together, which increases the local magnitude of B. This gives rise to a restoring force, which acts against the compression. The resulting fast mode waves propagate isotropically at the Alfvén speed, which is given by the B divided by the square root of mu naught rho. For the second term, it can be shown that this always acts in a direction to reduce the magnetic field line curvature, and for this reason, it is known as magnetic tension. The resulting transverse waves propagate along the magnetic field lines at the Alfvén speed. Lastly, I'd like to show an example simulation of ULF waves in the magnetosphere that I've done to put some of these ideas into action. The figure shows the Earth in the middle of the picture with two layers of magnetic field lines drawn out from the surface of the Earth in 3 dimensions. At the bottom of the plot is a map of the radial electric field in the equatorial plane. Waves in this simulation are launched along the magnetopore's boundary at a constant frequency of 3 millihertz. Now, both the magnetic field and the plasma density in the magnetosphere vary strongly with position, so this makes the Alfvén speed extremely inhomogeneous. This causes the fast mode wave to refract away from the inner magnetosphere and propagate along the dawn and dusk flanks. The map of the equatorial radial electric field shows 2 narrow peaks in activity in the equatorial plane and are And I positioned the layers of field lines to cross these peaks in the evening sector. These show standing shear Eifing waves that have been resonantly excited by the fast mode and are called field line resonances. The inner layer corresponds to the fundamental mode, and the outer layer corresponds to the third harmonic. In both cases, a peak in amplitude and phase change across the peak are clearly visible. These kinds of signals are routinely measured at various latitudes by ground-based magnetometers and can be used to remote sense the conditions of the magnetosphere, such as the distribution of plasma density. Well, that's all that I have time for, so I hope you enjoyed this presentation, and thanks for watching.